So just to let you know, the report has been started. So within the 4 pillars, system integration, robust, sustainable, affordable value chains, extending operation range and applications, and also 1 pillar or area on refrigerants and new technologies. And within each of the themes, we have an existing ongoing projects as listed in blue. Project 61, for example, heat pumps in positive energy districts, placement impacts on heat pump acoustics, and heat pump systems with low GWP refrigerants. So some of them are active and ongoing international collaboration projects, and the ones in red are projects and new starting projects, but also ideas which are on the pipeline. And if we look at the communication and our dialogue channels, we're active in publications through the project reports, results and findings from the different active projects that we have. We do publish our heat pumping technology magazine and newsletter, which I will tell you a little bit more in the next slide. We have an exciting and user-friendly new website, which is the heatpumpingtechnologies.org. We are active in performing several workshops and webinars, including what we're doing today, of course. And we are also active on social media. We do have LinkedIn and WeChat. One of the other activities within the HPT TCP is we do organize one of the largest heat pump conferences. In fact, 2 weeks ago, we had our conference in Austria, Vienna, which was attended by more than 800 attendees from different stakeholders, policymakers, academics, researchers, universities, etc., etc. And the next, in 2029, it will be in Copenhagen, Denmark, and we hope to see many of you in Copenhagen. And one other activity that we do, what we call is the National Experts Meeting. This is the place where we conceive most of the projects. So this is, we take a day around October, where we spend the whole day to develop a project from scratch, all the way to an active international collaboration project. So the National Experts Meeting perhaps is an ideal place for everyone here to attend and participate in developing some of the projects that we have. We do actively support the IEA in publications through providing data, but also providing expert knowledge. I briefly talked about the Heat Pumping Technology magazine. We have one of the prestigious technology magazine dedicated for any research aspects to heat pumping. We publish it 3 times a year, and those publication period, we select a theme based on a focus area or an interested area selected by the member countries. The one that we can see here is the latest publication of the magazine, which explored on flammable refrigerants in heat pumps, safety standards and best practice. In fact, I have seen several of the authors within this publication in the audience. If you want to download the latest issue, please scan the barcode. But it's a free digital magazine. And this is, in fact, one of the platforms where you can easily follow what's happening within the technology collaboration programs. You get to know what the progress is within the different active international collaboration projects. So the magazine provides an extract and a summary of all research related within the HPT TCP. So please scan and follow us and subscribe for those of you who has not subscribed. So this is the team within the Heat Pump Center. Please contact us if you do have any questions or you wanted to find out further informations. So that's briefly what the heat pumping technology collaboration program is about. But if you do have any further questions, please reach out and we can tell you more about it. So with this in mind, coming back to the main part of the presentations on the final results and findings from Project 59, heat pumps for drying. So the first presentation we will have is Verena. Verena, if you're ready, please share your presentation.
So now, hello everybody, here's Verena. Thank you, Metkel, for the introduction. And today everything is about heat pumps for drying. And first I would like to give a short introduction into Annex 59, which was, as I said, about heat pumps for drying. So the main objective was to evaluate the potentials of heat pump implementation into drying processes, with the key message that heat pumps are relevant for drying processes. And the scope was as well heat pumps in industrial environment as well as commercial and household applications like dishwashers or something like that. The annex lasted from 22 to 25, and there were several participants. So Austria had the operating agent, and there was also Switzerland, China, Germany, Norway, Sweden, and the US. The annex was divided into 5 tasks, starting with an overview on drying processes as they are, and assessing the theoretical optimum in task 2, and then going to the more practical side with task 3 on the monitoring of existing dryers with integrated heat pumps, and giving a market overview in task 4, and of course dissemination in task 5. So I will start on the theoretical side with assessing of the theoretical optimum and looking into the existing drying processes, and later on Quadin will give a more practical insight into the realized use cases. And finally, Michael will talk a little bit on how to implement a heat pump. So why should we at least use heat pumps for drying processes? Drying processes are very energy intensive in general. And looking on these products here, the drying is often the most energy intense step in the production chain at all. Drying is needed in a lot of different industries, like food or animal feed, but also in ceramics, chemicals, and of course in the paper industry. Drying is a large share of energy need there. The needed temperatures for drying processes often range between 100 and 200 degrees Celsius, so which is fitting to market available heat pumps. And the source for the heat pump is already there, because you can use the moist exhaust of the drying process as the source of the heat pump, which is advantageous because the source is then automatically available at the same time you need the energy for the drying process, and also on the same location. For the drying processes, there are a lot of different technologies available. So what we here see is mostly the industrial dryers, and we see the common range for the dryer temperature and the needed heating capacity for different drying technologies. And as we can see, A lot of drying technologies are fully inside the range of suitable market available heat pumps. So for example, belt dryers, which are used in the food and animal feed industry, as well as tunnel dryers, for example, used for bricks, and also the paper dryers. They are below this 200 degrees Celsius in drying temperature so that we can supply the energy with a heat pump. There are on the other side dryers that need higher temperatures, like example the flash dryer, which is for very fast drying. And in general, of course, lower drying temperatures are beneficial for heat pumps, and we can achieve these lower drying temperatures with a higher residence time inside the dryer for the product. So here we have a very basic drying process. Usually the drying agent used is air, so that is very common. You will hear afterwards from Philip that there are other possibilities for the drying agent, but at the moment, most of the drying processes are using air as a drying agent. And the fresh air from the environment is usually heated to the desired drying temperature using electricity or natural gas, which we call here residual heating demand. And inside the dryer, of course, the product is dried by evaporation of water, and the exhaust air, moist air, higher temperature, warm, moist air, is then usually rejected to the environment, and all the energy that is used for evaporating the water is on this way lost with the exhaust air. Here, there are so far no heat recovery measures implemented. So this is what we will use as a reference case for the theoretical considerations. To increase the efficiency of such a drying process, we can add, in the first step, a cooling zone for the product. So the hot product is leaving the dryer and is cooled by the fresh air. And the fresh air is, by the way, heated a little bit. And the second option is to add an air recirculation, which is reducing the overall mass of needed fresh air and increasing at the same time the outlet moisture of the air. To further increase the energy efficiency, direct heat recovery could be added so that the moist, warm exhaust air is used to preheat the fresh air in a direct heat exchange. So you can recover the sensible heat of the exhaust air. And this has a large potential for drying processes which require high temperatures and have high exhaust air temperatures, because then the temperature difference between the fresh air and the exhaust air and this heat exchanger is large, and you can recover a lot of heat. And the final step is then the implementation of a heat pump into the drying system. So finally, the fresh air is first heated by the cooling zone, afterwards heated by direct heat recovery, and then heated by the sink side of the heat pump. If the temperature of the heat pump is not high enough to run the drying process, there could be still some residual heating needed for the dryer inlet temperature. On the exhaust air side, the exhaust air is first used for direct heat recovery and then serves as a sink for the heat pump. In this case, heat pump is implemented using water cycles as well on the sink side as on the source side to provide enough energy for the heat pump to run the whole drying process. Usually condensation on the source side of the heat pump is needed so that the exhaust air temperature need to be cooled down below the true point. In this case, the true point is then decisive for the source temperature and so has a large influence on the COP of the heat pump. So important question is now what COP could be achieved using a heat pump in the drying process. And we try to get a first estimation using the Carnot approach. So Carnot COP is just depending on the temperature levels in the heat pump, where we have the hot temperature, which is on the sink side, and the cold temperature on the source side. Of course, in a real life heat pump, you would not achieve the ideal COP for the Carnot process. So you would have a certain efficiency, Carnot efficiency, which we assume to be 0.5. And then, of course, you need these both temperatures, the high temperature and the cold temperature. And the sink side temperature is depending on the needed dryer inlet temperature. And for sufficient heat exchange, we added 5 degrees Celsius for the heat exchanger. And we did the same on the cold side, on the source side of the heat pump, where we said that the true point is decisive for the temperature there. So we assume that the cold temperature is 5 Kelvin lower than the true point. And then you can create such a map where using your parameters for the drying process, you can have a first estimation of the COP that you would achieve when adding a heat pump into your drying process. A little bit more detailed estimations you can make using the drying toolbox, which is an online tool we developed during the Annex 59. And this tool is available via the link. It is for free, so you are invited to try it out using your own drying process. There is an underlying base model in Daimler Modelica, solving material and energy balances. There is no drying kinetics included into this drying toolbox model. So you should know the parameters of a drying process before you use it, so that you can input the needed temperatures and so on. And then the drying toolbox will calculate needed energy input and the potential for different heat recovery measures that you could click on to implement or not. So here is a snapshot from the input panel of the drying toolbox. You see that you have to input there the parameters for product and air, like moisture and the amount of product and air. You could add some losses. Of course, there is an important parameter, the needed drying temperature inside the dryer. And we used this drying toolbox to investigate some typical drying processes. And we did some assumptions. So if there is a heat pump used, the second law efficiency is 0.5. For the direct heat recovery, we assumed that there should be a temperature difference between the hot and the cold side of at least 20 degrees Celsius. Product cooler is cooling product to 35, and the fresh air is coming into the process with 25 degree. And we neglected thermal losses of all the drying processes and the dryer itself. But you could add some other assumptions if this would fit to your drying process more. So by clicking on calculate in the drying toolbox, the base model is then calculating material and energy balance for the inputted drying process, and you get as an output such a nice flow sheet of your drying process, and this also provides energy consumption for residual heating and fans if you add recirculations. Drying toolbox calculates the conditions of the exhaust air in temperature and humidity, and if you add a heat pump to your drying process, there is also the heating capacity and the electricity consumption for the heat pump calculated by the drying toolbox. So first example that I want to show you today is a spray dryer for starch. So spray dryer is working that way that you add some liquid on the top. The liquid in the liquid solve there is your product. All the water is evaporated and the product is leaving the drying chamber as a solvent here, as a particles down there. The basic process in this case is needing 160 degree as an air inlet temperature, and the air outlet temperature is still very high with 95 degree. And the product is entering the dryer very wet. So as I said, it is still a liquid phase, and product is leaving the dryer hot and very dry. So then by adding the different heat recovery measures, we get the different energy demand for this drying process. The reference without any heat recovery measures is nearly in 1.4 for the specific energy consumption, which is the energy demand divided by the mass of evaporated water. And this specific energy consumption gets better by adding step by step the different heat recovery measures. So in this case, the exhaust air is at a very high temperature and low moisture. So there is some potential for recirculation and a large potential for direct heat recovery. So if we, for example, add just the direct heat recovery to this process, the specific energy consumption is lowered to around 0.8. And then we investigated two configurations for a heat pump. The first option is to fully electrify this drying process by adding a heat pump that is capable of supplying 160 degrees Celsius, which is the needed drying temperature. But this is resulting in a quite low COP for the heat pump of around 1.5, but leading to the lowest possible specific energy consumption. Maybe a more economic configuration would be a heat pump supplying just 125 degrees. So then there is still residual heating needed in the drying process, which is then natural gas probably. But the COP, of course, is a lot better, and the electricity consumption is smaller. And the specific energy consumption is nearly the same as for the high temperature heat pump with 160 degrees. Finally, the drying toolbox is also providing a Sankey diagram, so an energy flow sheet for the drying process you edit there. And this is the Sankey diagram for the scene spray dryer with the heat pump providing 125 degrees Celsius. So there is still some residual heating needed. And we also have the electricity input for the heat pump. But we see that a large part of the energy inside the drying process is recovered by direct heat recovery, which is the red flow here, and the heat pump, which is the green flow down there. Still, there is a lot of energy leaving the dryer with the exhaust air. The heat into the product of the spray drying process is very, very low amount, so that is the reason why the product cooler does not have such an input on the energy consumption. The second process I want to show you today is a tower dryer for corn. So it's a very simple drying process. The corn is added on the top and the warm air is flowing upwards and the dry corn is leaving the dryer down there. For this drying process, the needed temperature is much lower. It's about 85 degrees Celsius for the inlet air. The outlet air is, of course, also very much cooler than seen before and also a little bit more moist. That is the reason why, in this case, direct heat recovery is not possible, because the exhaust air temperature is not hot enough to still heat the fresh air coming into the dryer. So we assume the minimum temperature difference of 20 degrees, which is not given there. So there's no potential for direct heat recovery. But caused by the lower drying temperature, the potential for heat pump implementation is, of course, very large, with a good COP of 2.4 in this case. And the specific energy consumption is decreased from around 1 kilowatt hour per kilogram to 0.4, which is energy saving about 60%. So to conclude, there is a high potential for energy savings in drying processes. Of course, the implementation of a heat pump shows the highest potential of savings up to 61%. And there is also the potential for fully electrification of drying processes, which then gives a fully green drying process if you use green electricity. We also have seen that the potential for a product cooler and recirculation and direct heat recovery is also there, but not that large as for implementing a heat pump. During Annex 59, we developed this drying toolbox, and again, everybody is invited to try it out. It is there on this link. For more information, of course, you know the project homepage of Annex 59. So thank you, that it's from my side. Are there already some questions regarding the drying toolbox? Or is there something in the chat? I cannot see the chat.
No, I am monitoring. So thank you so much for the exciting presentation, Verena. Any questions from the audience? I have not seen any question in the chat. Any questions, please raise your hand and we can elect. Yes, we have one. Listen. Please go ahead. Daniel?
Okay, hello. Daniel Stoll from OST. Just one question. In all your examples, you assumed humidity of 0% at the inlet. So then, yeah, you also need a dehumidification at the inlet. How
Yes.
would it affect the final results?
So yes, this is a kind of a simplification to be comparable through different drying processes. Of course, if you use ambient air, there would not be zero humidity in the inlet air. This humidity in the inlet air adds up to the added humidity by the drying process, which increases the COP a little bit because of a higher dew point of the exhaust air. So higher humidity on the exhaust air is in general beneficial. So yeah, if you know your own drying process and the ambient conditions, just add low humidity for the input air into the drying toolbox. At the end, the input humidity with the ambient air is much lower than the added humidity by the evaporation, so that the impact is not that large if you change the input air. So that is why I took this simplification for this comparison here.
Okay, thank you very much.
Thank you. Perhaps one question. Perhaps I can ask one question, Verena. I had two questions, perhaps. So you presented about the toolbox. Have the simulation outputs been validated against measured data from any of the Project 59 case studies?
So the drying process, the drying kinetic is not included into the drying toolbox. So there is just material and energy balance calculations in the base model, which cannot be wrong, of course. And the heat pump efficiencies and such things, they are taken from Annex 58, now 68. So the assumptions for Carnot efficiency for heat pumps and such things. Of course, in the real world cases, the achievable energy savings are always a little bit lower than in the theoretical optimum caused by losses and things like that.
Absolutely. So perhaps a follow-up question to, I'm sure there are several interested listeners in the audience. Now we're talking about, finalizing Project 59, and we have this exciting tool that has been developed within Project 59. So what happens? What are the planned next steps after Project 59 closes? Who maintains the tool afterwards? What happens to the tool?
So the tool is currently running on an AIT server, and the plan is that we as an AIT would maintain the tool for the next years. Maybe it would be included in our technology hubs on the AIT homepage, but the tool will still be available after closing of Annex 59, and the plan is that AIT would care about that.
Right, that's good to know. Well, thanks once again, Verena. We'll go to the next presenter, Philip, if you're ready. So Philip will be presenting about heat pump assisted superheated steam drying. Please, the floor is yours, Philip.
Hello, everyone from my side. I hope you can see my screen now. I'm Philipp Hofmann, a scientific researcher at the Fraunhofer IEG, a German institute for applied technologies. And I'm active in the field of high temperature heat pumps, and my contribution or our contribution to the annex was in the field of heat pump assisted superheated steam drying, which is, as Verena has already mentioned, a more specific and not that commonly used form of drying, but it is very energy efficient and especially beneficial when it comes to heat pump integration. So this should be mentioned in this annex as well. So let's get started. When we talk about the general properties, we talk about an atmosphere without or with low oxygen. This can be beneficial for some sensitive material, and that is the main reason why superheated steam drying was initially used, because oxidation, for example, can damage the taste and quality of some products. At elevated temperatures, we also have a faster drying speed compared to hot air drying, as we are also above the inversion temperature. The inversion temperature is the temperature above which a superheated steam drying process has a faster drying rate than a hot air drying process. And this is mostly due to the effect which is described in the table below, we have here the isobaric heating capacity, the CP of air, in a attractive temperature range and of superheated steam. And we see that the superheated steam has a significantly higher heating capacity. This means to evaporate the same amount of water, we have a reduced temperature glide. And this will also be beneficial energetically. And when it comes to the processes and materials, here is a collection of some food processes where superheated steam drying can be used without, for example, damaging the taste due to no oxidation. It is especially used for chemicals and industrial processes, especially in the fields of chemicals when it comes to detergents and pharmaceutical powders, where a fast and sterilized drying process is absolutely needed. And one can say that all in all relevant hot air drying processes could have or already have a superheated steam counterpart. So on the next slide, I will just go quickly above this slide. We will talk about the cons of hot air drying. And here I can present you the Mollier diagram, which gives an information about the enthalpy and the humidity ratio and the temperatures and the relative humidity of the air. And we have to consider that the humid waste air after the drying process is a mixture. It's a mixture of steam and dry air. And this means when we extract energy from this source, that we have a temperature glide. So this is a bit exaggerated as we don't really see such glides, but if you have a huge amount of enthalpy generated by cooling the outlet air of the process, at first, for example, we stop the process maybe 10 to 20 kelvins above the dew point. Then we have the sensible heat of the air. Then we start with the dew point, and then we have the condensation process. And when it now comes to heat pumps, this is a con. Why is that? It is mainly because of the fact that the heat pump efficiency is generally mostly described by the lowest temperature on the source side. And this is always the lowest temperature here after this temperature glide. And this is the first reason why hot air drying processes usually have a lower potential COP than the equivalent superheated steam drying process. And now let's get into the topic of the superheated steam drying. Here we have the temperature enthalpy diagram. And now we can see the regions where the drying takes place. So this is here in the orange field. This is the gas zone. In this zone between, for example, 120 to 240 degrees Celsius, the relevant drying processes we conducted theoretically in this project can take place. And where do we now get the energy for superheating the steam from? This energy is then, for example, generated by condensation. So we condensate steam at a higher pressure level, and then we generate isothermal latent heat. And this heat then can be used via a heat exchanger, for example, to superheat the steam atmosphere. And what we see now, as we always have steam, water, so to say, not a mixture, a pure refrigerant or a pure fluid, pure medium, we don't have any temperature glides. And this now enables relevantly higher COPs. But this has to be also mentioned. It is usually at a higher temperature level. The components and the equipments are usually more complex and more costly. And this, of course, leads to higher investment costs. But we will talk about those points later on. And now here, based on a literature review, one potential configuration for a superheated steam drying with mechanical vapor recompression is given. So let's start with our superheated steam drying model. This, for example, is a model of a belt dryer, and this model is, as previously mentioned, based on mass and energy balances. Here we have the wet product, and then here we have the dried product at the outlet. And here in this zone, we suck up the superheated steam, and the superheated steam usually is assumed to have at least 20 Kelvin superheating to the dew point, or to the dew line in this case. Then the steam is divided into these two paths. This path here is the, let's say, internal loop, where we have the direct reintegration of the superheated steam, which was also proven to be energy efficient on the previous slides for hot air drying. This is also the case for superheated steam drying. And we have the potential to go through these MVR stages. Those are open loop compressors, and those are also considered to be a form of an open loop heat pump. So here we have assumed 3 stages. They could be also 4, they could also be 3, or they could use a single screw compressor. In this case, a turbo machinery was selected, and we use condensate for intercooling. This is absolutely needed when we use water as a refrigerant or as a medium for heat transfer. And then we have here the internal thermal recuperation, where we have here on the one side the low pressure superheated steam being superheated again, maybe to a superheating of 100 Kelvin, by condensating the high pressurized steam here on the other side. And this is now an open system where this is discharged to the environment. A fraction is used for the intercooling. And what we also have is, because we have to close the overall energy balance, we always add electrical energy here. In the 0.5, we also have the potential that a fraction of the low pressure, low superheated steam can be used as a heat source for other processes. And I'll give you some numbers later on how much this is and in what cases this can be relevant. So to check out the thermodynamics, this here is the pH diagram, and this just shows the process inside the MVR stages. Don't you worry, those are 4 stages here, and I showed you 3 on the other side, and the number of stages always depends on the desired superheating temperature and on the product and its temperature needed as well. So here one can see that we have in all stages relevant superheating, although we only have a small pressure increase, and therefore this liquid subcooling after each stage, or in some cases when you use blowers even during the compression, is considered. And this model was used to calculate all the COPs and all the efficiency in combination with these mass and energy balance superheated steam drying chamber model. This process here in this case was the process to dry wood pellets, and here the superheated steam was sucked up at 130 degrees Celsius, then was compressed to above 200 degrees Celsius, and here the condenser would be applied, and this condenser would be able to superheat the steam which was not compressed in the stages again to up to 200 degrees. Let's get into the more technical aspects. So now we talked a lot about the thermodynamic benefits, and we were on a theoretical approach. And now I would like to go a bit further into the technology which is already available and the compressor selection for those processes. Those are just examples. There could also be other components, other companies supplying these components. But here we have the 3 main existing technologies that could be used for the mechanical vapor recompression system in superheated steam drying. Let's start with the blowers. The blowers are quite simple. They are an axial turbo machine, and they usually have very low pressure ratios, 1.1 to 1.4. And this usually leads to the need to have a cascade of various blowers. They are comparable cheap, but they have then very high space and room requirements. So they also offer the possibility to have a direct injection or an intercooling after each stage. And those are already market available products. When we then shift to the turbo machines, we just have the same type of machine, but we just change the geometry of the blades. So we don't have axial blades now, we have radial blades, and they increase the deliverable pressure ratio up to 2, which means for the same pressure lift, fewer stages are needed. They cost more. They also have an intercooling, but don't inject it into the turbo just after. And they are also market available products. And this now, last but not least, is a twin screw compressor machine. Here we could generally achieve the highest pressure ratios. 3 to 6 are feasible, and they are also cooled sometimes by oil. This wouldn't be capable or wouldn't be suitable for this open loop structure. But here we could also use water. And if you follow the link here on the source, you will see that this picture was rendered as a prototype for our research project Steam Screw, where the Fraunhofer IEG is developing together with some industrial partners this screw compressor for high temperature heat pumps. And this screw compressor could also, because it's oil-free and very compact, it needs no second stage, just one stage is enough. This can be used then, for example, in the future in those processes. Fraunhofer also conducted a market analysis, a comparable analysis of the existing heat pump market in 2025, where all relevant distributors and manufacturers submitted their data. And if you check out this link, there's also an English version available. It's the info hub for high temperature heat pumps. You can use several filters, and you can also select the open loop or closed loop structure. And this is what you will see, or at least this is the data you will get. You can also get the contacts and the web pages of the manufacturers. And here the data are presented in this graph. Each dot is a heat pump with its maximum temperature and its maximum capacity. And you see here that especially in this area, so at the elevated temperatures where the superheated steam drying processes usually take place, we see some blue diamonds, and those are the open loop systems we now talk about. And you see that they are, especially in the range where we talk about drying processes from 500 kilowatts to a bit more than 10 megawatts, there are already existing solutions. And I would say in the future, there will be more manufacturers, more competition in this field. So you will generally see maybe more products even. So when it comes to the real application, unfortunately, we don't have any real application in this part of the annex, but there is one very crucial point, and this is the handling of contaminants and of particles. So as you have seen, we had an open loop cycle, and here in this case, it would be possible that some particles from the product itself or from the dryer could be sucked into the compressors. So this could have some negative effects. If you use oil, for example, in screws, you could have a contamination of the oil. But what is even more crucial and critical is that abrasion and erosion of the blades, as those are components rotating at a very high speed, can damage your compressor. And what you also have, which is always a problem in heat pumps, but it's definitely solvable and feasible, are wall deposits and heat exchangers. So we now derived 2 potential measures against particles. You could use a cyclone separator, or you could use not an open loop, but a parallel separate closed loop cycle. And I will show them and explain them to you on the next slide. So here, this on the left doesn't change much, but we just apply a cyclone separator here. So particles and dirt would come off here, and here a cleaner or clean superheated steam mass flow could be sucked into the compressors. But this is not 100% safe, of course, because we still have the open loop system. And here, this could be an alternative cycle. We just add another evaporator here. And here you see now we don't discharge this amount here to the environment, this amount of condensate. This could also be beneficial when it comes to wastewater handling. We have a throttle added, so now we have just really a closed loop system installed. What we have in both cases is we have here an additional pressure loss in the cyclone, and of course here, because we have a pinch point in the evaporator here. And this would lead to a bit lower COPs, but don't you worry, a safe system operation is more crucial than the ultimately best COP, especially when you think about the fact you can see on the next slide that we have a very low specific energy consumption and very high COPs. So based on literature data and with our models also based on literature and the assumption I can show you here, 3 different processes which are commonly used were analyzed, and we used CoolProp for the modeling. We assumed turbo compressors with a maximum pressure ratio for each stage of 2, an isentropic efficiency of 75%, and a minimum of 20 Kelvin superheating in the superheated steam drying process to maintain enough time and enough kinetics for evaporation and heat transfer. And for the simulation, we so to say used process parameters, especially for the humidity rates of the wet and dry goods. And we, so to say, did a worst case assumption. Why worst case assumption? So we assumed that we use the European electricity mix with its typical given carbon emissions for 2025. And we assumed that we use a new modern gas boiler. In many cases, they aren't that efficient. And this gas boiler has an efficiency of 95%, which is only feasible when you use a new application. All the apparatuses, they only have 70 or 80%, for example. And what we didn't assume, of course, was green electricity, because if you use green electricity, you would immediately decarbonize all your process. So you would have CO2 reductions of 100%. This is great, but maybe not for this analysis. What you see for these processes with the different temperature range, beet pulp, food, paper, in this case tissue due to the high temperature, and wood chips, we see that we always enable significant CO2 reduction, even if we have a low COP, comparatively low COP, but here this would mean when we have 1 bar drying atmosphere, a lift of about, let's say, 130 to 150 degrees, or adding to the pinch requirements in the heat exchanger. So this is very high lift application. And what is also crucial, the recuperation potential. I mentioned that before, that fraction of the mass flow can be used outside of the system. Why is that? So we bring in new water with the stream of the wet product into the system, and this is then converted mostly into steam. So this is in the mass equation. What we also have is we use electrical energy for the compression of the steam, and this is immediately converted into heat. And this means that to just fulfill the stationary operation of the system, we have to let out some mass and some heat. And this is attractive because you can see this is the temperature level, not of the mass flow itself. This is the condensating temperature of the steam, which is now useful or can be used here. And if you have this low COP process, you use lots of electricity, or comparably lots of electricity. And then you have the potential to recover 50% of the heat outside of your process as a source, maybe for other processes, at a condensating temperature, because we have 1 bar in the superheated steam chamber of 100 degrees Celsius. So this is also a very attractive and very valuable heat source for the, let's say, the decarbonized industry of the future, and has to be mentioned in this case. This always depends on the losses the process has itself. So if you have a well-insulated dryer and a well-insulated process, this is higher. We assume 20% heat losses here, which is typical and conservative. But if you have a very bad insulated process, you would be able to recuperate a lower amount of heat. But this would also be critical in the fossil fueled counterpart, because there you would have to burn more gas or oil. So last but not least, let's talk about the conclusions and learnings. So many products could or would benefit to switch to superheated steam drying because of the low oxygen environment. So it's available for many products. The plants are costly, complex, and not that easy to install. So this is, of course, it's an obstacle for the rollout. Superheated steam drying processes don't have a glide at the source side. This is valuable when it comes to heat pump integration, and the drying medium, the steam, is also operated as a refrigerant, which makes it even more efficient. Open loop heat pumps are required, and if you have any considerations about dirt, you can use a cyclone, or you could change to a closed loop system by maintaining just the same blower or the same screw architecture. We saw that this superheated steam drying process assisted with heat pumps enables significant CO2 reduction potentials, even without green electricity. And please keep in mind that those reduction potentials I showed you are compared to a superheated steam drying fueled by gas. So if you would compare it to a hot air drying fueled by gas, you would even save more. And you also have the possibility, if you have a well-insulated process, and especially when the COP is low due to the high lift, you can use more valuable waste heat at a higher temperature level. And in some cases, we don't did an exact analysis, but I would assume that the high COPs over a long period of time, especially in countries with higher electricity or higher gas prices, they are able to be competitive, even though you have higher investments and higher installation costs. So I'm thanking you for your attentions, and I'm looking forward for any questions or comments.
Thank you very much for the thought-provoking presentation, Philip. Any questions from the audience? 1 or 2 questions before we proceed to the next presenter. Any questions?
Just one question. Can you go back to the references, please? Thank you.
Did you want to see the sources only, or did you have a question there?
Oh, that was...
Okay, yeah. So perhaps maybe one question for you, Philip, if I don't see any questions from the audience. I was wondering how does the heat pump assisted superheated steam compare against MVR for, of course, for the same duty in terms of both energy and also capital cost? Take us through that, or talk to us about that.
Yes, we can talk about that. So here you see we did this to avoid dirt or particles, but this is a closed loop architecture. You could use another refrigerant, for example, a hydrocarbon or an HFO. Here, generally, you would achieve lower costs, especially for HFOs. when you don't have to think about the ash rate class and ATEX precautions, but you would generally achieve lower COPs. Why is that? So water has the highest critical temperature, and in this very high temperature range we talk about, it is the refrigerant of choice when it comes to the COP. So you would have significantly lower COPs due to the higher temperature range where you operate the process. So I would assume that for, let's say, 80 to 90% of the cases I can think about, water would be the best selection.
Right. Thanks. Any other questions? Okay, well, once again, thanks a lot, Philip. We will go to the next presenter. Cordin, if you're ready, please share your presentation. So Cordin will be talking to us about heat pumps for industrial drying processes, an overview of realized use cases. So please, the floor is yours, Cordin.
Yes, hello. Please, can you not share the screen anymore? Or I try to yeah, share my screen.
We can see it.
Now you can see. Okay, great. So hello, everybody. I'm Cordin from Eastern Switzerland University of Applied Science. I'm going to talk about more practical examples of heat pumps in industrial drying processes. I try to give an overview of some case studies that we derived in this Annex 59 project. So realized examples, representative cases, want to try to summarize some success factors, and then some summary. I made a big summary table that you may look at later on as well. So the heat pump integration is a possible measure for energy savings and CO2 emission reduction. So in principle, from theory, we can achieve up to about 80% energy savings by changing from an open cycle to a closed cycle system. So Verena showed it before, and Philip as well. So we replace, in principle, or we close the loop and replace gas-fired heating by electrical-driven heat pump technology with electricity, which is hopefully renewable. So we have 10 demonstration cases from the project 69, which are available on the website. So this includes pulp and paper, air-dried beef, beet drying, animal feed, food drying, fish meal, brick drying, starch drying, and biomass. And here you see the companies and the countries where these cases are realized. There is also the link then to the different data sheets you can follow up later on. And now I want to demonstrate this a little bit with visuals, try to bring up some pictures and so on. I start with the Transpac heat pump from France, which was installed in a pulp and drying application at Vapour Greenfield, Dalkia Group. So here we see a paper dryer, and it has the drying air and then a condensate. This condensate is used to preheat the fresh air. Then you have further the condensate, and here the installation of the heat source or the evaporator of a transcritical heat pump that generates 580 kilowatt, then 155 degrees to heat up this air. So this is the principal diagram of this integration. The Transpac heat pump is a container which has piston compressors. It is installed outside of the factory. The refrigerant is the HFO. And what is special about this case, this is transcritical. So not transcritical CO2, but transcritical HFO refrigerant. And if you are familiar with TS diagram as a heat pump researcher, you can see here the diagram. And here the transcritical cooling of this HFO refrigerant, which allows to heat up the air to high temperature. So it's a suitable solution, this transcritical technology, to heat up an airstream with large glide. The COP that is achieved is higher than 3.5, so it seems to be an economic case. And I would expect that this technology gets further implemented into the market. Another example is from Switzerland. This is actually where I come from. This is about air-dried beef. So it's a little bit different drying process. Here we have a much lower temperature level. So in Switzerland, we are here in the Alps. So like in Austria, we have here the mountains and dry air. So this dry air in the mountains is very beneficial for drying. And our former generations dried the meat in the dry air in the Alps. And this is the motivation. Actually, here I come from this place. So it's very much, I like this meat very much. It's a geographical identified protected brand, this Bündnerfleisch in German. It's dried above 800 meters above sea level, and it takes long. It takes about 3 to 6 months to dry this meat. And there's a big production, 2,500 tons per year. So the drying temperatures are around 12 to 18 degrees. So it's called cold drying. And there is also a sweetening phase at 21, 26 degrees for that meat to develop the flavor. And so you have here some pictures of these dried meats, and then the drying program, the temperature over the time. And what is special about this drying is that they use CO2 heat pump booster systems and CO2 heat pump to use the waste heat to dry this meat. It's a little bit a complex diagram. I just want to give you the message that we use here a refrigerant which is natural, a natural refrigerant, CO2. Temperature levels are much lower. There is the possibility to use the CO2 cycle also for cooling. So it's a freezing room for the meat. And then here the air around 40-degree hot water glycol loop. So to generate this air. Now to spray drying. Spray drying is another interesting field of technology. Here we see on the left a big scale spray dryer for spray drying milk permeate. So here you see the powder. Milk permeate is the aqueous solution of the milk that includes the sugar. And this milk permeate powder is used in bakeries to make different food products. So it's very energy intensive. And the message is there are some solutions now with heat pumps to integrate them into a spray dryer. And this is a solution from GEA, the so-called AdCool system. So we have here also a CO2 heat pump that has 2 gas coolers. There is a intermediate secondary loop for hot water. This hot water goes into the air stream to heat up the air for the spray dryer, which is shown here. And then the cold side of the heat pump, of the CO2 heat pump, can be a cooling loop. So both sides of this heat pump are beneficial. So we achieve a high COP, so heating and cooling COP. Another heat source that is used is the exhaust air as a heat source for the CO2 heat pump. This has been realized in Denmark at the test center from GEA. So here we see pictures of this CO2 heat pump with 2 piston compressors from GEA Bock. So the CO2 heat pump can go up to 150 degrees, let's say. It generates 130 degree hot water, and this is then used to heat up the air. So the capacity of this pilot is 90 kilowatt, but it shows in principle that it works. And now it has been scaled up at the company Arla Foods in Denmark to higher capacity, to a factor of 10 times larger, so 900 kilowatt, almost reaching 1 megawatt heating capacity for the heat pump. Here we see the installation, side with the spray dryer on the left, in the middle the heat pump installation, and here on the right the heat storage vessel tanks. So the principal concept is similar. So we have here the CO2 heat pump, the cooling loop for the chip, which can be used for cooling, and then the air heating up to 120 degrees with the CO2 technology. Then later on, steam, the electrical heating for further upgrading the heat to maybe 200 degrees. So this has been integrated in this SHSD 315 spray dryer, 900 kilowatts capacity, COP of 3.6. What is interesting is that this heat pump can react very quickly. So we see here a temperature time diagram, and here spray on, and it takes only a few minutes to reach the air temperature after the air-cool technology. Here we see the electricity demand, and here the air temperature to the dryer. So the message here, it's full operational in a few minutes, in about approximately 14 minutes, which is important for spray drying applications. And they can reduce here with this system the CO2 emissions and save a lot of natural gas. Another example is the electrified aqua feed dryer from Gallon Counterflow. So here we have a dryer that dries, in this case, salmon feed, and it has several layers. And what is needed is hot air to dry this feed. And what is done, we have here the heat pump installations from Combitherm, in principle 4 units in parallel, and they generate 120 degree hot water, which goes then into this dryer. So you have see here a video where this hot water goes in, and in principle, this is a fully electrified dryer. So that's the main message here. It's possible to, at that temperature levels, to eliminate the fossil fuel heating. Here we have more data, another picture of this dryer. We have here the 4 units which generate 3.5 megawatt of heating with Combitherm. They use HFO refrigerant and 120 degree hot water, some beet compressors from Germany, screw compressors, and the COP is about 2.8. Looking at the whole, let's say, drying process, where 2/3 of the time the temperatures are from 40 degree heat source, which is the exhaust, humid air, I didn't tell that, to 120 degree, and another operating mode from 40 degree to 90 degree, which gives then an average 2.8 COP. The savings, 3,000 tons CO2 per year, and energy savings also very, very substantial. Then Agrana starch drying. Here we have also this heat pump. This was developed in the dry efficiency project. The air enters here for the dryer at 30 degree. It is heated with water, and then this water is then also used as a heat source for a heat pump that can generate then about 140 degree to further heat up the air. Further steam is still needed later on. So this part here is the heat pump. You see here this container solution. The technical information here, they use 2 refrigerant circuits, so 2 heat pumps, let's say, in circuits in parallel. The beet also screw compressors and HFO refrigerant. Here we have now some COP data. The COP as a function of the temperature lift. We know this relationship very well. And we have here different data points and also smaller points from one of our publications about 9 years ago. And the Carnot efficiency of 50% as a line. And you see here the black dots, the 1, 2, 3, 4 numbers. These are the CUPs that are achieved in this Agrana start drying and also in Wienerberger rig drying. So these are monitoring data, real data, so it confirms the CUP values from also other industrial heat pump installations. Then another example in the paper industry, this is the largest steam generating heat pump, I think at the moment, actually from Turboden. So this is in Finland, where they have quite, let's say, low electricity price. So the business case was favorable. And this reduces the fossil fuel steam generation. 19,000 tons of CO2 can be reduced, and it's a 12.5 megawatt installation, 20 ton per hour steam. Here you see the temperature conditions. It's quite a high lift, and the CUP is up to 2. What is also interesting is isobutane as a refrigerant, hydrocarbon fluid. Then last but not least, in my presentation, some slides about push to heat. This is a European funded Horizon project where we as OST are also part. And this is an installation at the paper factory in Felix Schoeller Group in Weissenborn in Germany. And what is used is a heat pump that generates steam from SPH, a German company. So they use exhaust humid air as a heat source, 46 degrees, 690 kilowatt. And then with this system, upgrade the heat again to 123 degrees to steam for the drying process. Here we have a little bit a bigger picture of this heat pump. So you see here 4 compressors. It's a cascade cycle with 2 refrigerants. On the bottom cycle, it's R515B, synthetic refrigerant with screw compressors from Bitzer. And in the top cycle, 2 piston compressors from SPH that runs also with HFO refrigerant. And here on the right, the steam generator heat exchanger that directly generates steam by condensing this R1233ZD refrigerant. The CUP for that temperature conditions 2.3. They also save a lot of CO2, 230 tons and 2,400 megawatt hours of energy. There is also a link to the fact sheet from Push to Heat. So I would like to summarize. Now I made a big table, but these are the cases that I presented that are also shown in this Annex 59 project. We have here different products. In the paper industry, milk powder, feed, food examples, bricks, starch, biomass. I didn't mention it, but there is also a fact sheet on that. The refrigerants that are used, you can see here, we have HFOs, also this transcritical example as an interesting example, CO2, but then also ammonia water. I didn't go into detail that in that case, but also natural refrigerants for drying and so on. The capacities are in the several hundred kilowatts heating capacity range, and some are even in the megawatt scale. So the heat sources are typically exhaust humid air for of the dryers, some waste heat at some temperatures which are suitable for heat pump integration, And then the heat sink temperatures, you can see here, the list go up to 140, 160 degree, 180 as well, or 120. A special case, the air drying from Switzerland at 43 degree cold drying. The COPs you see here, they are quite high for this drying applications, at least higher than 2. Some go up to 5, 6. And key outcomes. So, so transcritical heat pump, that's something unique. For the dryer, we have simultaneous cooling, dehumidification, and heating. For the spray dryer, we can reduce a lot of fossil fuel. Then, energy savings, CO2 reductions. We can generate steam. So there are examples where the steam heat pumps are shown. This brick production is electrified. So fully electrifying the processes is a major outcome and goal. So reducing fossil fuel dependence and so on. So this is a summary of that. I'd like to conclude with some takeaways. First, most of these applications that we see are in the food and feed drying. This is evidenced by different cases shown here. Then the high temperature heat pumps now deliver also steam. This is also possible. We have here some examples. Natural refrigerants are becoming more preferred solutions, but there are also HFO solutions that are presented. Then industrial heat pumps can cover almost the entire drying temperature range. So it still needs a little bit gas or fossil fuel drying to reach, let's say, 200 degrees and so on. But some solutions are really fully covering the temperature range. And large scale is also commercial, as shown the Turboden paper heat pump, steam heat pump in Finland, or some others like this ammonia water heat pumps in Norway. I didn't show actually the ammonia water systems, but you will find the fact sheets. And integration of the heat recovery is very crucial. So to capture the heat from these exhaust air streams or from refrigeration systems and so on. So thanks a lot. I'd like to acknowledge here some projects, also a Swiss dedicated project about heating and cooling. We have here push to heat. We have the Annex 959 and also project. So actually it's project 59 and project 68 about high temperature heat pumps, and also Zimba, another heat an absorption heat transformer project. So that was it from my side. Hope give you an introduction into these cases and open up for any questions.
Thank you so much, Cordin. It's really amazing to see the wide range of use cases of using heat pumps for a range of applications of drying. Really exciting. Questions from the audience? I see hands up. So, Charles.
Yes. Hello. Thank you, Cordin, for the very nice presentation, as always. I have two quick questions, or maybe not so quick. The first one is, do you know how the manufacturers will react to the F-gas legislation, since many of them seem to be using HFOs continuously? And the second question is, do you know in this project if the footprint of the whole system was an issue, and if the cases that were chosen because there was space available or not? Thank you.
Thank you, Charles. Good question about the refrigerants. I think F-gas regulation, this is clear. We have to change, and especially in Europe. I think the second question with the footprint is also related to the refrigerant as well. So you can imagine hydrocarbons need more safety measures. so probably not so easy for integration into existing systems, but I cannot say I'm open for both. You have seen the electrified beet dryer from Gallon Counterflow. This is a new installation. So, and in principle, the heat pumps are like an add-on technology to the dryer. So it's a very individual, I think, this footprint question and also the refrigerant question. I mean, I'm a university employee. We want to go into a renewable future, I would say, for our next generation. So there is definitely a trend towards natural refrigerants and also noble gases like your technology.
Thank you, Gordon. Rainer?
Yeah, thank you very much for the very interesting presentations. In one of the first slides, there was an overview, and there what I saw was also the tumble dryers in the residential areas. Is there in some of all these presentations of the work of this annex, is there something done in the tumble dryers, or is there a presentation about tumble dryers?
Thank you, Rainer. The tumble dryers we analyzed a little bit in the beginning of the project 659, especially in Switzerland. We have this trend towards, well, not only in Switzerland, but to go to propane with low charge. But the focus was then more on these industrial cases. But we could follow up on that for sure for the residential applications. Maybe Verena can also comment on it, why we focused then more on the industrial. I think it also depended on the partners from the different countries.
Well, Cordy, but I think you can learn a lot of things of the tumble dryers, because there is a air cycle where you reduce the humidity and you are makes the drying process with air with low humidity. And that is a drying process which is very successful and concerning the energy consumption. And to be honest, all what I see with the industrial ones, what you presented or all the other presented, was only to replace the production of high temperatures by a heat pump instead of steam process or something like this. But I could not see that someone is using this tumble dryer process, which is very interesting. You reduce the temperature. In a tumble dryer, normally you have 110 degrees centigrade, and we reduced it to 50, 40 degrees. And that is an interesting thing for using a heat pump for a drying process. I missed a little bit this basic idea, which is, and for example, the tumble dryers are the most produced heat pumps in domestic areas, because, for example, in Germany, they have 600, 700 pieces a year for tumble dryers, at least. Thank you for your attention.
Thank you very much. I think the tumble dryers is a really important market, and we should really focus more. We could have focused really more on that. Definitely, and especially integrating the heat pump technology in the dryer. So very, how do you say, this is integrated in the dryer, in the cycle. That's most efficient, definitely.
Thank you.
Okay, as always, thank you for the interesting comments and question, Rainer. So I think at this point, we will continue to the next presenter, Cordin. Thank you so much. I always enjoy your presentations, so thank you. Last but not least, so now we've looked at the theoretical background, we've looked at the actual use cases. Now we will look at a presentation about from ideas to execution, guidelines and obstacles from successful heat pump implementation. Michel, the floor is yours.
Thank you very much.
So I see we're already a bit over time. I try
No
to make it
worries.
short.
Take your time.
So what I'm presenting is the results of the workshops we had during the project time. So it's about obstacles and incentives for heat pump assisted drying on an industrial scales, where we identified 3 stakeholders, and learning from their challenges, we implemented a procedure guide how to implement the heat pump. So starting with the first stakeholder, that's the dryer operator. That's the one who pays usually. So the biggest obstacle is probably the economics. So they have the high capex to implement the heat pump. In a world of volatile energy prices and a low margin business, this can result to long payback time. They have a technical risk because they need to implement the heat pump somewhere into their running operation. So this might be a challenge. And also they have probably limited knowledge on heat pumps. And as they do implement the heat pump, their supply chain might get bigger. There are more people involved, so things get more complex. But on the other hand, there are also strong drivers like sustainability requirements, CO2 regulations, the customer demand for greener products, of course, and increasing policy support. So we see that there is a business case, but the operators need confidence and reference projects and reduced complexity. The second stakeholder we looked at was the dryer manufacturer. So also they are probably experts in drying and not in refrigeration. So there's a knowledge gap. The customer probably wants the cheapest solution, but the most efficient solution would probably require a bigger dryer to allow for lower temperatures, for example. So we have a design conflict. And also changing the product requires high R&D costs, and the possibilities for demonstration are limited. But on the other hand, customer demand is growing, as we see, and manufacturers who gain experience early can really penetrate the market with off-the-shelf solutions. And then we come to the heat pump manufacturer. Once again, they're probably experts on their heat pump cycle and not so much on the drying requirements, but this can be a problem as we have maybe batch production, varying source and sink needs and things like that. Also, as we have seen in the presentations before, the temperature level is often going towards 200 degrees, where it's conventional heat pump is reaching its limits. So we probably need steam compression maybe. This again adds complexity and different suppliers. And also there's a market risk, as your reputation could be tainted if you are taking part in a not successful demonstration project. But once you kind of develop the successful reference design, there might be the potential for replication. And for heat pump manufacturers, the process integration knowledge is probably the key thing that becomes the ticket into this very attractive market. So now we talked about all these concerns and problems. How do we come to a real project? Within the project 59, we developed this procedure guide. It's not a rigid checklist. It's more of a roadmap how to get to a heat pump assisted drying. And this is probably as we do our project within AIT ourselves. So we came up with this flowchart and we'll go through it step by step. We'll start with the use case. So before any calculations, we need to understand what is the project we're trying, what the qualities, the volumes, the temperatures. As the food dryer and the biomass dryer and pharmaceutical dryer, textile dryer, they all have different requirements and could all be driven by heat pump, but it's a different question for each one of those. And if this step is unclear, everything downstream becomes a bit uncertain. In the box on the right, you can see some helping hands through your project development. So once we defined the use case, we need to understand the current system. This is where good measurements are essential. So we need to know all the temperatures, humidity levels, losses, energy consumption, and things like that. Even the question, is a heat pump necessary, or can I do it via direct heat recovery? This is where pinch analysis could help. And once we've understood the process, we need to understand the market. So as we do it, we talk to different suppliers for heat pumps, heat exchangers, whatsoever. Because in our experience, 1 hour discussion with someone who already solved one of these problems can save a lot of engineering work. And here I want to refer to the Großwärmepumpenportal that was already mentioned, and our colleagues from the other projects, like the already finished 58 or the now running project 68. Once we've set all those points, we can actually start designing. So in the conception design phase, we don't aim for perfection. We just need reasonable estimates like electricity consumption, COP, temperature levels, airflow concepts. So in this phase, the goal is to identify promising concepts and also eliminate unrealistic ones. And here, reference once again to the drying toolbox that Verena presented in the first presentation. Once we've set those boundary conditions, the inevitable question comes, does it actually make sense economically? So we take into account investment costs, operating costs, seasonal performance, things like that. And also we establish reference scenarios to which we compare all our calculations. And we also test sensitivity to avoid to have a perfect looking project in your spreadsheet, but once one boundary condition changes, everything falls apart. Once we've established that, the engineering reality starts to kick in. So we have to consider different sides to the project, like space constraints or noise, ATEX, fire safety, things like that, monitoring concept. So this is the next step. And once we are done with this, we take a step back and review the whole system and ask questions like, does it fit into a long-term strategy? Can we keep the production volume that high as we want to? Does it align with our sustainability targets? Things like that. And this is where a clear go or no-go criteria is defined. So once again, if we all put this into a loop, it looks like this. And I also want to highlight that this is an iterative process. So it's not straightforward, but a lot of going back and forth. Yeah, so as a conclusion, I think that the heat pump assisted drying is not the question of technical possibility, because the technology exists, but the challenge currently is successful implementation. Thanks.
Thanks a lot, Michel. Any questions from the audience? Okay, we have a happy audience. Michelle, no questions. I don't see any.
I'll take it.
Yes, any questions? So once again, thanks a lot, Michelle, for the presentation. Before we finalize our today's webinar, perhaps Verena, if you want to say any final words, perhaps where they can find the final report from Project 59. If there are anything that you wanted to perhaps highlight and inform.
Thank you, Metkel. Thank you, Rice, for organizing the webinar. Final report, as you mentioned, it is still in the making, in the finalization phase, one could say. So I hope that it will be out during summer. There is the Project 59 homepage. I'm sure you all know it already. There are the latest news, so I'm sure you will find there all the things we were talking about. You find there the link to the drying toolbox. We will also upload there a link to the video. So the webinar was recorded, and the presentations will also be there. Just check out the homepage, I would say.
Okay, thanks, Verena. So please join me in thanking all the presenters, Verena, Philip, Cordin, and Michelle. Thank you for the exciting and also thought-provoking presentations. I've really enjoyed all the presentations. I want also thank perhaps my colleagues within the Heat Pump Center. Emilia, thank you for your support behind the scenes. I have seen you briefly in the video, and I've also saw Monica and also our chair, Stefan Renz. Thank you so much. If you do have any questions, happy to provide further further responses to any questions that you might have. And with that, I think we will close the webinar today. Thank you, everyone, and thank you so much to the presenters once again. Have a good day.
Thank you.
Thank you. Bye-bye.
Bye.
Thank you. Bye-bye.
Bye.
Bye.
Maybe Metkel, a short question. So where would you put the recording so that we can link it from the Project 59 page?
Yeah. So we have few options. Normally we upload it in the HPT YouTube channel if it's a video recording. And then from the YouTube channel, then we can link the YouTube link into the Project 59 page. We may write just a short news article about this final webinar. And in there, then we can list all the presenters and then access to the presentation. So you can have it on the Project 59 page, and then we can bounce it to the actual main landing page of our website. So if you could either, perhaps if I have all the presenters here, if you can send me your presentations or send it to Verena, and Verena, you can share it to me, and then we can upload it on the website for Project 59.
Yeah, so I already have it except for Cordin.
Okay.
So Cordin, maybe you can do a smaller version, so because you said it is about how many megabyte because of the lots of photos and the video.
He has left.
Oh, okay.
Yeah.
Okay.
But
So then I will reach out to Cordin, and then I send you all the presentations.
Okay. Yeah, and I will
then
prepare a short article and share it with you, and you can add any dimensions that you want to add to the article.
Yeah, and once you have linked it on the YouTube channel, just send me the link, and I can link it on the project homepage.
Definitely. Yeah, we'll do that, and we share it on our LinkedIn platform as well. in all the social media channels that
Yeah.
we have.
Sounds good. So, Philip, your presentation I can take as I have it, I think.
Yes, the PDF would be good.
Yeah, the PDF, of course. Yeah. Yeah. Fast.
Okay.
Thanks.